Okay. So now I am going to, or I have, exploited technology to stop the recording after I messed up for a bit. Got a drink of water, got a snack. Now let's look at our actual example. All right. So here I am. Oops, I messed up again because if we don't have matplotlib, that needs to not be there. All right. So here I am. I am importing numpy as np. Again, that's just giving the module a different name, but it's ubiquitously done, right? So we don't have to write numpy out every time. I'm importing random. I'm initializing my first and second layer weight matrices, right? So W1, right, is this one. It is the 2 to 3, right? The layer 1, 2 input, 3 output layer. We can see that it is a 3 by 2 matrix. And then W2 is the 3 input, 1 output, second layer, and we can see that it is a 1 by 3 matrix. And I am making sure that these are float 32, 32-bit floats, because neural network math very frequently does not need to be high precision. So we can save ourselves both some compute cycles and some memory if we use 32-bit instead of 64-bit. Actually, recently, a lot of people have started using 16-bit half-width floats. I do not, frankly, know if NumPy will do that on an x86 CPU, right? But at the very least, we can use a 32-bit float to save ourselves a little bit of time and memory. Okay? Then, I once again am defining that derivative, right? That's just a function where I'm going to store my d of tan h, right? Which is my activation function. Then I'm building a data set, right? So I said before that we're going to get a list, right, of tuples of an input and a label, right? So this is a list of a list-like thing. It's a little bit of a complicated data layout. So make sure you sort of understand it, right? It's this. So at each step, I am going to create an X, figure out what the label D should be, and then store that tuple in the list, right? So I'm dealing with a binary rule, right? I've got two variables, each of which has exactly 2 states, so I can very easily just directly enumerate them, right? And notice that they are real values, not Booleans, because the input to our neural network has to be a real value and not a Boolean, right? So here I'm just enumerating all combinations of A and B, where A and B are binary variables. I am packing them, A and B are, yeah, they're binary variables, but they're type, anyway. I'm packing them into a NumPy array, right? I'm doing it as a column vector because my input has to be a column vector, and I'm storing that in INP. Then, very straightforward, I'm just using the built-in OR, right? If A or B, then output equals 0.75, right? And remember, I'm not using 1 because that because tanh asymptotically approaches this at positive infinity, and that causes our weights to blow up. So I'm using 0.5 as our sort of output label for true. And I'm packaging that in a 2D, right, with wiggle quotes, array, right? It is a two-dimensional array, or matrix, in the sense that it has two indices, but there's one thing in it. And again, that's because we want to use the matrix product and the dimensions have to line up, right? Otherwise, the output is 0, right? And so hopefully we remember enough about like the rules for Python variables that we know that we do not have to pre-declare this up here, right? This code is going to work, right? We don't have to pre-initialize or declare this elsewhere because Python is nice and friendly. Then I insert into the array, into the list, right? Here's my data set list. I insert into it, okay, I thought I was using a tuple, here I'm using a list, but I insert into it a list containing the input and the output, right? So that's what I'm winding up with. It's because I'm dumb and I'm using a list. I'm winding up with a list of numpy array, I've got exactly 4 of these, right? One for each of the values of A and B, right? Then I've got my learning rate, which I have picked a slightly larger version, or slightly larger value of, for no interesting or valid reason. In the forward pass, I'm still making a random choice out of that data set, and I am unpacking it, right? The first thing is going into X1, and the second thing is going into D. And the first thing is the input, and the second thing is the output, so that's correct, right? Then, I'm computing that matrix product to get my pre-activation, and I'm applying the nonlinearity to the pre-activation, and I'm doing that again for layer 2 to get my final output M, right? This time I do compute the loss directly, and I store it in this list. That is so I can do that graphing later, which we'll see in a minute, right? Then, oops, I'm computing my error, right, the way I was doing before. And remember, even though this makes sense as an error definition, remember that that is actually coming from that calculus, right? That error, whoops, was a term in computing the derivative with respect to a weight of the loss, right? That's where we're getting that D minus M. So it makes sense as an error, but it's justified by that little bit of calculus, okay? We are computing our weight updates and storing them in these sort of delta matrices. So dW2 is properly read as delta W2, or deltas for W2, change or update. We are computing our backprop error using the rule before. We're computing delta W1 using our sort of single layer update rule. And then we are applying our deltas times our learning rates. And then down here at the very bottom, is that going to be a color? Let's find out. Down here at the very bottom, ooh, it is. Down here at the very bottom, I'm just going to see what our network produces for each and every input, right? So I'm just going to iterate over every input and label in the data set, and I'm going to compute the final output. Whoops, ignore that. Ignore those, sorry. I'm going to compute the final output, and then I'm going to print the input, the label or correct value, and the output, right? And I think I've talked about those F strings before. Those are a fairly newish Python feature. It's just an easy way to print the values in brackets, right? It's an easier way to do string formatting. I'm hoping that's pretty self-explanatory once you see what it does. And we'll explain what that B1 is. That shouldn't have been there. It's for later. Whoops. So if I run this, there's the full path of my Dropbox. Good. Didn't take too enormously long, and we see pretty much the results we saw before, right? So that 7.4 bunch of 9s is the target minus some really, really tiny epsilon. What's the symbol for epsilon? I'm blanking on my Greek symbols. I think it's that, right? And then this one down here is our target of 0.75 plus some really tiny epsilon. So, good. Now, suppose that we want to draw this, to graph it. Well, I have already, I don't want to do that. So, we can use the library matplotlib. Now, matplotlib and the submodule pyplot might not be installed by default, so you might have to use either Anaconda, so conda install matplotlib, or pip install matplotlib to install it. I should have thought about that. I cannot ask them to do a new image with that installed by default because that'll erase anything you've got saved in the old one. So just do conda install or pip install matplotlib, and that should work. But, so I'm going to import matplotlib. I've already got this nice list of my losses. And I'm just going to do plt.plot losses, which is this list right here, okay? And plt is what I imported matplotlib.pyplot as. Now I'm going to run this in stretch, and it finishes. So if you are running this at a normal console, you will now see a window with a plot. If you run it in Spider, the plots get saved up here. So here is our loss. This is our loss for OR. Down here, it's oscillating a little bit, but notice that it still and then settles down very quickly, right? Now, let us suppose that I would like to see what our loss looks like for XOR. Basically, all I need to do is replace this with an expression of XOR. That is going to be if A and not B, or B and not A. I love Python, right? Yeah. I love Python. You can just write sort of like an English description of what you want, and pretty close to right. Okay, so jumble thought. I love Python because the correct code so often winds up sounding like a description of what you wanted to have happen, right? This code is extremely readable, right? But that's the rule that we want, right? If we get A and not B, we're going to get the one case, or the true case. And if we get B and not A, we're going to get true. Otherwise, we're going to get false, right? So, if we run this, I forgot a colon. If we run this, and again, pause for thought. Once again, we see our target minus some really tiny error in these cases, and our target of 0 plus some really tiny error in this case, right? So it worked. And when we look at our plot pane, we see once again, the reason this looks like it's shaded is because it's bouncing, right? But it very quickly, sort of after oscillating for a little bit, settles to pretty much the right answer and then just stays there, right? So there are our two, there is our two-layer feed-forward network learning a basic logical rule, complete with a little added extra bit where we graphed the output. This is quite useful. Matplotlib is awesome. It is a superb visualization library. It is a very good thing to sneak a little bit of practice in, right? If you work in this area a lot, then familiarity with Matplotlib will pay dividends, right? Good old Matplotlib.